Hello and welcome to Hadoop Exam Interactive Training. In this session, we are going to cover HDFS design, where we'll see where to use HDFS and where not to use HDFS. And secondly, we'll see fundamentals of HDFS, where we see what is blocks, name node, and other services means in the HDFS. Then we will see rack awareness philosophy in the HDFS, then how to read write files in HDFS file system, and and then deep dive in HDFS federation, high availability of HDFS, then parallel copying using disk CP, etc. And in last we also see some HDFS command line interfaces. So let's start with the HDFS design first. Okay, so in HDFS design, let me write the topic name HDFS design. So as we have discussed previously, as soon as your data volume grows, your data keep increasing and it reaches like in terabytes or petabytes, it is difficult to store this whole file in a single machine. This whole file in a single machine, because the capacity of this single machine is 250 gigabytes. So what to do now? So in such situation, we can divide this file and store 250 gigabytes in each machines, and we could have 4 separate physical machine where we can store this file. Okay, so these are the 4 computers or 4 machines uh, which is capable of storing 250 gigabytes each. So your file can be stored in 4 parts to this 4 computer. So the system which actually store your single file in multiple machines is called distributed file system. File system. So from the Hadoop, it is called Hadoop distributed file system when you want to store your file in a Hadoop based environment. So and once this file stored on multiple machines, so there is a communication required among these machines. So and to handle this communication, there's a lot of networking comes into the picture. But however, if you use HDFS, so you don't have to deal with networking coding. It is already handled by the HDFS client and HDFS itself. Okay, so this way we can say you divide your whole file into multiple part and store on but different one or more machines. It is required distributed file system. So Hadoop uses one distributed file system which is based on Google file system, and this is called HDFS. So let's say uh, this is the design of we can say how basic design, not exactly in-depth design uh, of HDFS. So let's see benefit of using HDFS or where to use HDFS. As some of things we have already discussed in this, like very large files, as we have already discussed, then you use HDFS. Secondly, streaming data access. What streaming data access means? Streaming data access means whenever you want to read data in lot not lot, in bigger volume. So you need some system which can give you high throughput to read bigger volume of data, and rather than reading a single record. So and what I can say, like here, if you just need to write once but read many times, so you will read the whole data in huge volume, gigabytes at a time. So in this case, this is good to use. And secondly, the you don't want to use expensive hardware, because as we have already discussed in our previous session, it's like HDFS works on commodity hardware. So you want to save your cost, IT cost, let's say, then you can use HDFS. So these are the basic things where we should consider using the HDFS file system. But the places where we should not consider the HDFS, like whenever you want to have low latency access. Low latency access means whenever you want to read from whole file system single record in milliseconds or something. So in such scenario, HDFS is not good. Then you should consider something else like HBase database, which is also based on HDFS, and we will see in later session how to use the HBase and what is the purpose of HBase. So the basic things here, like if you need faster access and delete, insert or something functionality, then you should consider using HBase. So whenever you require low latency access, please avoid using HDFS. Second is lot of small files. If you have thousands of or millions of, sorry, not thousand, millions of small files, so then it is not good to use HDFS. Why? We'll see when we let's see, there is a one master node name node which store metadata information in RAM. We'll see in detail how this for each and every file. So there are millions of files, and each and every file's metadata is stored in the RAM, and the RAM capacity will not be able to handle so many files. So we should consider in avoiding in the HDFS file system when there are a lot of small files. The next is parallel write or arbitrary rate. Then avoid using HDFS, because HDFS will always write, suppose your file is already written up to this, at the end of this file, and keep adding on this file. So you cannot write at the start of the file, or parallel write is possible on this file. So whenever you have to write in parallel, then kindly avoid using HDFS. So these are the points where we should consider using HDFS and where we should not use HDFS. Let's pick up next topic, that is fundamental of HDFS. HDFS. So first pick up the blocks. In each and every file system, even you consider Linux based or something on Windows file system, every file is in underlying file system is divided into the blocks. Whenever you have to write a bigger file to file system, is internally divide into the blocks, and generally block size is 512 bytes on the most of the operating system, and this blocks is actually written to the file system. And whenever you read it again, so your file system will merge this whole block and return you the file system, or block by block it will return you the file, and so your client will actually create a single file and again process the same file which you have already written. Similarly, HDFS also has a concept of blocks, but here block size is very huge. Almost 64 MB is the default block size, and some of the clusters are having 120 MB of block size. This is depend on the requirement and reading writing capacity and cluster size. Many things needs to be considered when we consider the block size. So suppose you have a file, this is the file which size is, let's make it rounding, 6400 MB. So whenever you send this file to store in HDFS file system, it will be first divided into the 100 block by the HDFS client or HDFS itself, and these blocks are stored on the HDFS. So this is the block of the HDFS file system. Suppose assume your file is smaller than 64 MB. This file is less than 64 MB. Then what happens? Then will it occupy the full one block of 64 MB? Suppose your file is 50 MB and you want to store this file, so it will occupy the whole 64 MB. Answer is no, because HDFS is optimized for this purpose, and it will make the block only 50 MB size in such case. So even the file smaller than 64 MB, it is create a block of the smaller size and stored into the HDFS. Let's see the next fundamental or concept of HDFS. This is daemon services HDFS. HDFS has three daemon services running. One is name node, second is secondary name node, and third one is data node. So these are the daemon services. Let's pick up the first one is the name node, and then we'll see the others later after that. HDFS is based on Google file system, and the architecture is almost similar. So the architecture of HDFS is master slave architecture. So there is always one master in HDFS, that is called name node. This is the name node. This is the master, and there are some slave nodes. So slave are always more than one. So these are the slave node. Let's see here, only 4 name slave node I am creating, and this name node this slave node are called data node. Okay, so this is DN1, this is DN2, something like DN3 and DN4. So this 4 data node. So this is master. You can see the king, and these are all slave. And so what is the purpose of each master and slave node? uh, so let me draw on the clean piece this thing. So suppose you have a one file, like file 1.txt, and which size is like mm, let's say 64 multiplied by 3 equal to 192 MB. So it would be divided into 3 blocks, A, B and C, and you want to store this file. So there is a name node first. This is name node, and there are 4 data node. And you want to store this file into the HDFS. So this all are on HDFS. Okay, it is, we are discussing HDFS only. So your client or client HDFS client, and this is you which using HDFS client and want to store this file. So you first, your goal first contact with the name node and ask, I want to store this file. So in this situation, HDFS will guide, like there is, it has the information, like there are 4 data node, tn1, tn2, tn3 and tn4. Based on some information it will return, like you can write this file on 1, 2 and 3 data node. So now this client will directly contact to data node 1 and pick up this, ask to data node 1 to store in tn1, and it will store block A in TA, and it will return, it will ask to be ready to store this block A to be stored on this node, and it will return yes, I'm ready, you can send me the block. Okay, so this way this communication happen. We will see later on how actual full write happens on the HDFS. So whenever this information is sent to data node, so this name node has metadata information where the whole file is stored. So it will has information like file 1 is stored on A, B and C, data node 1, 2 and 3. And suppose you similarly you have another file 2.txt and you want to store it, and similarly for simplicity assume it has E, F and G block. So it stored this block into data node 2, 3 and 4. So this is E, F and G. So it will has this metadata information like file 2 is stored on 2, 3 and 4. So this is the master node which has the whole information where the each file is stored on the cluster. So this is in, we can say this is bookkeeper which has the information. The most important thing here is like this whole metadata information is stored in the RAM. Okay, and suppose this name node crashes. So what happens? You will lose the whole cluster where the data is stored information, because this information is not persisted anywhere. So that is why in generation 1 Hadoop was considered as single point of failure. This is the disadvantage. Yeah, but there are a lot of work around, we can say, is there to handle this situation. We will see in next few moments. And other in generation 2, it is it is very well improved and handled in Hadoop to avoid such single point of failure. So this is the basic use of a name node and data node. So let's deep dive into this daemon services, and let me draw it again the same architecture and deeper a little bit more deep will go. So this is your name node, which has master, and generally your cluster look like this. As we have discussed, it would have rack. So let's consider we have two rack 1 and rack 2. Okay, and each rack has data node 1, 2 and 3, 1, 2 and 3, your D1, D2, D3, D4, D5 and D6. These are the data, and there is one core switch. This switch are networking switch. Okay, so this is networking switch, and again each rack itself has their own switch, networking switch. What is the use of switch? Let me first explain it. Whenever this node D1 want to talk to D2 and D3, so this communication happens. So they first go to this switch, and this switch has the information, and they contact each other like this. And similarly, if rack 1 want to talks to rack 2, then it first go to here and then talks to rack 2. So this way this happens. So this is the normal architecture of your normal HDFS cluster. So, and I wanted to discuss here something like replication factor. Let me clean it out, this diagram again. Replication factor. As its name suggests, you want to replicate a copy of your data. Replicate it. So as we have discussed, we have three data nodes, D1, D2 and D3, and your file, which is quite big, and you divide it in three blocks, A, B and C. And here we have replication factor value equal to 3. So your block A would be stored in this and this. Sorry, I mean to say this is also A and this is also A. So let me take one more data node here to understand more. D4. Okay, so because of replication 3, your one block is stored in A, D1, D2, D3. Now I wanted to store block B. So block B would be stored 2, 3 and 4, and block C would be stored in here and here. So this way each file block has been replicated at 3 places. Suppose this node crashes, then still we have copy of A here and B here and here. So this is quite resilient to any node crashes and master node name node immediately find it out, like node 2 is not responding, it has crashed. So it has information, like as we have discussed, metadata information, which block was available on D2. So whatever block was on D2, it will immediately try to copy this node 8 to this node 4, and the node B was on this, to make it again replication factor to 3. So this is the replication factor. So in case of any crashes or something, still the data is available and you won't lose the data. So this is the replication factor. So now let's pick up, next topic is rack awareness. Rack awareness means, like similarly as master node, like name node has information by which block is stored in which data node, and similarly there are rack, like let me type short R1 and R2, and data node D1, D2 and D3 are here, D4, D5 and D6 and D7. That's one more node here. So in rack awareness philosophy, this name node information is also there, like it has rack 1 and it has information 1, 2 and 3 node are there. Rack 2 has 4, 5, 6 and 7 node. So in case of whole rack is gone, so still, so this is the rack awareness, like it knows like which node was there, and from the metadata information it will get to know on which node 1 what block was available, on node 2 what block was stored, on node 3 what blocks are stored. So it can easily recover the whole cluster in case of any failure. So this is, we say, rack awareness philosophy. In case of any failure, it can recover easily. Let's say move to next daemon service. This is secondary name node. As its name suggests, it is not a passive name node. It's just confusing name. We can say what it does actually. If you, as we have discussed, this is the name node. It hold information in the RAM, all metadata information. What secondary name node say, SNN in short, it reads this log, whatever in memory, after in periodic interval, and this information somewhere, it's like not directly from RAM, it read from some edit log and namespace log, which is written in particular time interval, like we can say it's particular checkpoint service, and it reshuffle this whole log and name edit log, whatever is required, and store persistently in secondary name node. Similarly, in every checkpoint, CP2 and CP3, kind of each checkpoint is being created and stored over here. Suppose this node goes down or crashes. So first thing, it doesn't automatically, no automatic failover. First thing, admin has to come in between. They will pick up the latest checkpoint information and make this node, or they will copy this information in another node and create another master name node. So however, they are able to do this, but they definitely have lost some information, because this checkpoint will have been taken in some time before the node crashes. So that is almost certain you will lose the data. So this is, that's why it is not exactly the we can say passive name node, but however somehow you are able to get something back uh, whenever the main node goes down. So there are other alternatives is also available for the handling of single point of failure. We'll see uh, in few moment. Okay, so this is all about secondary name node, and secondary name node does heavy input output operation like shuffling of name node and namespace and edit block, and it also require use RAM. Okay, okay, so this is secondary name node. Let's see now the underlying file system. Sorry, underlying file system of HDFS. Underlying file system in HDFS. HDFS file system is actually an abstract. This is not actual file system. Underneath there is another file system, that is either ext4 or ext3. This is just a concept. We should not go in depth of this actually right now. So whenever your use file is divided into the block and you send this particular block to store to HDFS, what HDFS does is actually it won't store itself, it just redirect this and commit this block to ext4 or either ext3 file system. So this is the underlying file system of HDFS. Okay, so this based on this we can change the various configuration to make it different availability or kind of thing from ext4 and ext3 perspective. So these are the underlying file system. So as we have discussed a lot about HDFS file system, so and this is file system, so we need some command line utility to access this file system. Like in Linux, Unix we have, and even in Windows, command line utility to access the file. So the best thing about HDFS command line interface, it is almost similar to Unix Linux command line utility. So it has ls commands which list all the files as you do in Unix. There's next command mkdir, which is used for create directory. Next command is this is different command, copy from local. Its name suggests copy data from local, so your local machine to HDFS system, you want to copy this data, so you can use copy from local command and it will copy this data. Similarly, copy to local, this is copy from local, then copy to local from HDFS to your local file system would be copied. Then similarly, move to local, which completely move your file to the local file system. And there are some other command like rm for removal purpose, then del command for del something as we are doing in Unix Linux, then chmod to change the mode. Actually there is no executable, right? Executable mode is making any difference, so its command is still there for other purposes but not for executable purpose. And something let me clean it out again. Another command which will say set replication minus w to 4 recursively under this directory to subdirectory. So this is the command. Whenever, as we have discussed, there is a default replication factor is 3, but whenever you want to make replication factor to up or downward, you can put value over here like 2, 4 or something, and it would be changed accordingly. The replication factor will be changed. Okay, so this is all about replication factor. Okay, so let's deep dive into the how we write file into the HDFS file system. Writing the file in HDFS. Suppose you have file and which is divided in 3 block A, B or C, B and C, and there is a rack 1 has following data node DN1, DN2 and DN3, and rack 2 has DN4, DN5 and DN6 node. Okay, and this is name node. So your client code will ask name node, give me the information where I can store the data, and it will say you can store block A to 1, 4 and 5 node. So now this client could directly contact with the data node 1 and ask him to be ready. I'm going to store the block A on your machine, and DN1, and seems at the same time it also send the information like forward this request to another node 4 and 5. So this information will goes to, and this is also asked like be ready, the block A is coming and it will be stored on you. And similarly DN5, so this is low latency because this is inside the rack, and this is higher latency because this is communication among it. And as soon as it replies yes I am ready, this also replies I am ready, and this says yes I'm ready, so send me the block A, and it sends the block A and it will be stored over here. And once this stored over here, this after storing, this goes to node 4, it goes to here, and this after this it goes to on node 5, is stored over here. So this is completely synchronous, right? You cannot write parallelly. Once block A is written, then it again goes and asks for B to be write, and similarly it asks I wanted to write block B 4, 5 and 6. It return this information, and sorry it will be better 2, 5 and 6. So it will be block B will be stored over here, B here and B here, and similarly C. So this way the whole writing is happen into the HDFS cluster. And same way, whenever reading is something opposite of this, and this is self-explanatory, I believe. Suppose you want to read the file, you will directly go to name node A. It will give you the whole information where all the blocks of A, B and C is stored from their metadata information. After that, client will directly contact the data node for reading the file, and it will read file from particular like DN1 for block A, DN2 for block B and DN6 for block C. So it will say read from 1, 2 and 6 node, and it will start reading it and create the whole file from the block and return it back to you. So this is the reading of the file. So I'm not going in depth of reading of the file. This is almost similar opposite of writing the file. So now let's pick up next topic is HDFS federation. What HDFS federation means, as we have discussed, there is a master name and it stores whole information into the RAM. Okay, so there are millions of files are coming and needs keep increasing to stores, and after some time it is possible your whole name node RAM is full and you cannot further, even the cluster capacity is available. You have thousands of nodes, one two, like there's thousands of nodes in the cluster and cluster capacity is available, but your name node is full, so you cannot write the file. So in such situation, what in new generation of HDFS new support has been provided, like using the let me clean it up. You just create name node based on your requirement. Keep increasing the name node. This is name node 1, this is name node 2, this is name node 3, which take care of, like there is a one company which deal with the finance data, news and social media data. This all things is done. So you create three name node, one take care for finance to related things, one take care of news, and another is media, but still they all are having the same cluster because there are thousands of data nodes in the cluster, thousands nodes. So this has same communication in the cluster, this is also same communication, just they have metadata information related to finance, this has metadata related to news, and this has metadata media only. So this you can see here, like single name node responsibility is divided into three, so this three name node could have differently and lightly loaded, and they could have their own backup, like secondary name node something, it has their own secondary name node, it would have secondary name node as per sequence. So this is HDFS federation where you divide the whole single name node work, which is for multiple domain into multiple different name node. So this is HDFS federation. Next topic is high availability of name node. So as we have discussed in generation 1, there is single point of failure, but in generation 2 there is a possibility you can create active and passive node. So like you could have two name node, one is in active, another is in passive mode. What happens, like whenever a block is stored or something cluster come up, like the all metadata, first thing, like all metadata in the H name node is populated only when cluster is started, and each name node data node will say like I am having this block, I am having this block kind of thing. So this data node inform to name node. So whenever cluster come up, this all four data node communicate with the, like node 1 communicate with the name node 1, data node also communicate with the name node 2. Similarly 2 also communicate with both the node, 3 also communicate with the both the node, and so on it will go. So this both the node in the RAM has the same information, and suppose this node crashes, so automatically in few moments or some involvement of admin it can come up, and which is having the same information. So in previous case using the secondary name node we were losing some information, but using this configuration we are not losing any cluster information. Suppose this node goes down, still this node is available. So this is high availability which is available in generation 2 of the HDFS. So now let's pick up the last topic of this session is parallel copying of data using utility dist cp. What is that? Suppose you have one production cluster, another is your UAT cluster, third is your normal dev test cluster. So and the volume of data is quite huge on the production cluster, and you want to copy this whole data in UAT cluster, and similarly you want to copy this whole data on the test cluster. So it will take a lot of time to copy this whole data into the one cluster to another cluster. So there is one utility which comes with the HDFS, that is called DistCP, which is distributed copying, and which is possible in parallel. So you just write the command like this in Hadoop file system distcp from this HDFS URL, like name node 1 colon 8020 directory is foo bar to HDFS cluster is UAT 1 colon 8020 foo bar. Using this command you can parallelly copy the whole your HDFS data, and best thing is like it uses internally map radius to copy this data. So it can easily take care of anything fail or something, any copy fail. So it's quite resilient, and it will completely write in uh, so it's complete right, it even it is fail or something, so it will map reduce will take care of while copying and all this thing in HDFS cluster. So today's discussion we are finishing over here, and as we have dis- discussed today the following topic: HDFS design, fundamental of HDFS, where we have discussed how blocks are stored in the data node, and name node stores the metadata information, and secondary name node works like some checkpoint information is stored to bring back the cluster in case of name node failure, and some rack awareness philosophy we understood. So how name node can tell you like which node is storing which block something, and we have also discussed how to read and write from the HDFS. So this is just conceptually we haven't seen any API, which we will see in few next coming session, and we have seen the HDFS federations, like how name node can be divided based on their functionality, and new generation high availability we have checked, where active passive configuration we have checked. We have also checked like one utility which comes with the HDFS, that is DistCP, to copy data from one cluster to another cluster. And at the last we have seen the HDFS command line interface, which is almost similar to normally available command line interface on Linux or Unix box, and some additional command also we have seen, like copy from local, copy to local, etc. So thanks for listening to this session, we are finishing over here.